No mai haere mai, no te mini miti kati ranga oku te puna, no paniki oku mātua, Nick Smith, aho. So my name is Nick Smith, I'm the Vice-Chancellor of Te Herenga Waka. It's my great pleasure to welcome everybody here today. It's also my great pleasure to introduce Professor Nick Long. When you read bios of our academics, you see people who are brilliant thinkers and great contributors to technology. You see people who are builders of community and people who have built that community over many generations. And you also see people who have taken their ideas and brought them to a reality that transcends the proverbial ivory tower and brought them out into a context where they can add enormous value. And I think what we're going to see tonight is someone who has done all three of those achievements and is that quintessential modern academic. As you will hear, and I'm only reading from the CV notes and I'm continuing to live vicariously through those achievements, Nick is not only an extraordinary scientist, he's a leader of what is described as we walk through one of the jewels in the crown of the university. And as I've been promised by Nick himself just a few minutes ago, there's going to be a fascinating exploration of the use of technology, not just terrestrial technology, but extraterrestrial technology as we move into space. And I think that's both a reality and also a metaphor for Nick's own career and what we're about to hear. He's promised me there's going to be really good news at about 6:45, so I'm awaited with bated breath. But until then, with no further ado, it's my great pleasure to welcome Nick Long to give his inaugural lecture to the lectern.
Kia ora koutou katoa. Thank you very much, Vice-Chancellor, for those warm words. Just a few quick acknowledgements before I begin. I'd like to acknowledge my wife, Jane, who does a lot of extra work in supporting my career. She does the extra work when I have to travel and do those other duties. So she's someone who has really sacrificed. Thanks to all my colleagues at Victoria and at Robinson. It really is a team effort out there. What I'm going to talk about is very much about what our team has done over the years. Some of it will be my particular take on things, my particular work, but it's all been very much a team effort. It's been my great privilege to be the director of Robinson Research Institute since 2016, and I work with an absolutely fantastic group of very talented people. This is an old photo. There's now about twice as many as people as here. It's difficult to get us all together in one place now because we're actually across 3 sites. So getting all about 80 of us together is somewhat difficult. We whakapapa back through Industrial Research Limited and back to the DSIR, for those who know that. So the team was set up when Bill Robinson was the director of the Physics and Engineering Laboratory. We do mission-orientated research on electromagnetic technologies and materials technologies. We do way more than I could possibly talk about tonight, so I'll concentrate on the superconductivity, which is where we have our international reputation. So first of all, superconductivity was discovered in 1911 by Kamerlingh Onnes, a Dutchman. And it was truly surprising. Nobody at all predicted that the resistance of a material could drop to 0. And Kamerlingh Onnes immediately thought, what is this good for? So that's a phrase of our PVC Isan. What are you good for? What is our research good for? Kamerlingh Onnes realised maybe he could make very strong magnets using this material, which could conduct electricity without any resistance. Unfortunately, he had the wrong type of superconductors, so it took a long time, actually, until the right kind of superconductors were discovered, and there weren't useful magnets until about the 1960s. So what was found, actually superconductivity is not that rare. A lot of the elements on the periodic table are superconductors, and a lot more of them are superconductors under pressure in particular, or in particular forms. You don't have to memorise any of these slides. There's not going to be a test at the end, so just enjoy the pictures. There's one or two equations which I couldn't resist putting in. So there are a lot of superconducting materials have been discovered over the years. This is a timeline. Most importantly for our group, the so-called high-temperature superconductors were discovered in the 1980s, about 1987, and the team then at DSIR made some important discoveries, and a team was formed around that. There are many of these materials. Very, very few of them are actually useful as wires. And this is a characteristic of any technology. There are many things you can do, but actually making them useful in the world is a different story. So we'll talk about that during the talk tonight. So out of these materials, only about 5 of them form wires that you could actually buy commercially. And the main one I'll talk about tonight, one of the high temperature superconductors, is the yttrium-barium copper oxide superconductor, which we've been involved in the wire development of that. We also were involved in developing the BISCO materials. You'll see some of these materials are getting closer to room temperature, but they're under very high pressure. So again, they're more of scientific interest, not of practical interest. So YBCO, this is the crystal structure. So it's a ceramic material, a bit like a coffee cup, but it has this crystal structure. The superconductivity occurs in the copper oxide planes. So the electrons move through those planes in this superconducting state. It's not easy to come up with an analogy of superconductivity that's, that's easy to explain and is accurate. It's a quantum phenomenon of many electrons all acting together. But nonetheless, I'll have a go. So for the first time ever, here's an analogy. Imagine trying to get through a crowded concert, and getting through that crowd, you keep bumping into things, and bumping into things is losing energy, it's resistance. So that's our normal conduction. So is there another way to do the conduction? Well, you can crowd surf. So it's a cooperative behaviour. Everybody else is helping you get through, and you're not bumping into anybody. And for the nerds, it's 2 electrons together do the crowd surfing. So that's superconductivity. What that gives you is a material that can conduct without resistance in the DC state, and very importantly, it can conduct at very, very high current densities. So that's actually often the most useful property. So here we have modelled for us a superconducting cable in the right hand, and in the left are the 2 copper cables. So those copper cables would carry about 1,000 amps. The superconducting cable, depending on the conditions, can carry a couple of thousand amps. At very low temperatures even more, maybe 10,000 amps. So you can see the value in that in shrinking the size of large machines. Now, just to cover off one thing, the disadvantage that I'm sure you're all aware of is you have to cool the superconductors. So people always bring this up. Isn't it difficult to cool superconductors? Well, what you do is you buy a refrigerator. So we buy refrigerators. They're more expensive than your ones, but they work essentially just the same. They have a thermodynamic cycle. We attach the cold end of them to, say, a coil of the superconductor that we want to cool down. And this works fine. The refrigerators are very reliable. So that is not a problem, a fundamental problem in restricting this technology. It is something that has to be taken into account. So the materials were discovered, and then we did a lot of work developing them into wires. We did a lot of work in collaboration with American Superconductor in the United States, but we've also worked with other wire companies. And so today we can buy this wire. This is the YBCO wire. It looks just a bit like a thin copper film. That's because it has copper on the outside. So the structure of it is actually a complex layered structure, and that's because the crystals in the material have to be very well lined up. So you have to create buffer layers on which the crystal can grow to a very high accuracy. And then on the outside, you protect it with layers of silver and copper. The superconducting layer itself is only about 1 to 2 microns thick. So it is very, very thin, but it carries that incredible current density. So a centimetre width of this wire can, depending on the circumstances, carry 500 amps or more. So this wire, it's made by vacuum deposition systems, usually a sort of reel-to-reel process. So we've worked on some of those processes. In cross-section, it looks like that. So then what we often do is we want to measure the critical current capacity of the wire. And to do that, we developed what we call our Supercurrent measurement system. So this was developed particularly by Nick Strickland and Stuart Wimbush. And we now sell this system actually commercially. We've sold a couple of systems. And here's the good news. We're going to sell 3 systems this year. So the good news is coming early for the Vice-Chancellor. Our part of this, we make the measurement system, and our sister company HTS 110 make the magnet. The measurement system's worth about $400,000 income to us. So we're going to do 3. We have to deliver 3 by Christmas, but that's great that we've got some income. So, so what we do is the sample is put in the magnetic field. You pass a current through it, and then you rotate the sample. So what is of interest is the current capacity is limited. It's not infinite in these materials, so we need to know where that limit is. And it's limited by the size of the magnetic field, the angle that it's rotated to with this crystal structure, and the temperature. And then we collect a whole lot of data like this. And I particularly became interested in this data. So what you can see, this is a whole range of data at different temperatures. But if you just sort of look in the middle, you can see there's a peak structure in there. So when we started doing this work, I was particularly interested in this because I thought people don't really understand these peak structures and other structures that people had. And I didn't believe what they were saying. So, if you've got a peak, what you normally do in physics is fit a bell curve. That's what everybody does. So this is a toy which illustrates how you get a bell curve. In this case, some metal balls are being passed through a little grid, and they spread out and they form the bell curve. So they're very common bell curves throughout nature. And so if you look at them as x, so here's the couple of equations, you get this what we call a normal distribution, or sometimes called a Gaussian distribution. But we were measuring with angle, so we weren't measuring with x, whatever x might be. So you can ask another question. You can ask what angle on average did those balls travel through before they drop down into that distribution. And if you ask that question, what is that distribution, you get this rather strange equation, which can be derived with a little bit of mathematics. It looks a bit odd, so it looks a little bit like a Gaussian, but as the variance gets large, you get these strange shoulder shapes to it. And then I took various data and I fitted this, and it worked. So this was a very nice explanation of the physics of how this is limited. So I was very proud of this, and I thought everybody is going to love this in the field, and I'm going to get a zillion citations. Actually, most people didn't understand it, and some people were openly hostile. They did not want bell curves in their superconductors. They wanted something much, much fancier, and that was not good enough. So, and some people, of course, loved it, and so those are the ones I remember. So we then go from wire to coils. So we now need to sort of start moving towards magnets and so on. So we developed coil winding at the Institute of various types. And you can see here what we call pancake coils, solenoid coils, the long coil, the sort of long cylinder on the left there, saddle coils, which can be used for things like motors, are in the centre there. And I'll just briefly mention in 2004 we spun out a company, HTS 110. So they, since then, have been very successful making bespoke magnets for different applications, very high-end scientific applications throughout the world. So they've produced some really unique magnets and done extremely well, and we continue to work with them. We also developed something I was quite involved in, something called Rebel cables. So a single wire can carry usually maybe 200 amps, depending on the conditions. And for large machines, you often want a conductor which can carry thousands of amps. So if you think of a very large motor or transformer, you want thousands of amps. So to take that wire and make it into a cable, we had to develop this technology called Rebel cables. You have to actually make the wire into a serpentine shape and then wind it or sort of weave it together. So that was a very challenging project. I luckily hired some very good engineers. I think I hired the two best engineers in New Zealand. So Peter Beck made the first machines and Rod Badcock made the second set of machines to do that. And then we go on to constructing magnets and devices. So here you can see a set of coils being put together into a magnet, which I'll talk about briefly. So the first application of this technology, what is it good for and what are we working towards, is MRI technology. So this was probably the first technology where superconductors were used that made an impact on the public. So in the 1960s and 70s they were used for scientific purposes, but the public would have first encountered them probably in the late 1980s, 1990s with MRI machines. So MRI is a technique where the signal comes from actually the water molecules, the nuclei of water molecules in your body. So it's completely benign. You can have as many MRIs as you like. There's no effect. It can give you very high resolution data on your soft tissues and even on the functioning of those soft tissues. So it's a very active area of research where people are continually pushing the boundaries of resolution and what you can diagnose from MRI. So we made, first of all, two small portable systems of MRI. So this demonstrated that we could use this new superconducting wire with the cryocoolers and we could get good quality images. The first system actually was the lower system, 1.5 Tesla system. Was for extremity MRI, was the application we had in mind. So that's imaging, hands or arms, feet. And then we built a subsequent system which was aimed at what's called preclinical. So this is imaging small animals and so on. So they're very successful technically. They didn't quite find a market for them. So we then went on to another project. This is a project we've just completed over the last couple of weeks, actually. A head-only functional MRI. So functional means it can see actual changes in the brain and image those as they're happening. And what's unique about it is this idea of the magnet just comes down over your head only. So it's a little bit like a helmet, and there's actually a port through which you can see. So that means you can read things, look at things while you're having an MRI done. Your arms and legs are also a bit free, so you could possibly play the piano, something like that. People can then image what's going on. So the research capacity of this machine and potential is really quite extraordinary. So that took a number of years, and this is good news for ESAN. The magnet is in Minnesota and it's working. So congratulations to Ben Parkinson and his team for getting that over there and getting it working. So I think the potential of this is really enormous, and possibly even therapy. I can imagine actually being able to look at changes in the brain as you're doing particular therapy, even if you want to really let your imagination run wild. Now I'd like to talk about fusion and this possibility of putting the sun in a bottle. This is something which is right now driving the whole superconductor industry quite strongly. And people are constructing these very space-age looking tokamaks in order to test confinement of plasmas at very, very high temperatures. Some of you may know there's the ITER project. So this is a long-running international project. It's a 20 billion euro project in the south of France. They're also building this superconducting magnets and a superconducting tokamak. Their magnets are much bigger than ours, as you can see. And I don't think we'd risk the finances to try and build one of these. Now, if you've followed fusion, you may have heard that fusion is never going to happen. So I thought I'd just sort of address that issue a little bit broadly, because it sort of goes to the question of what research do we do, and how do we evaluate whether we should be doing research or not? How do we select projects? So I thought I'd talk about that a little bit. This question of when will we have that technology? So the way I like to explain this to the staff at Robinson is we need to think about our technology, and that's the new technology that we're creating, but it's also the old technologies that have to go with it. So, for example, we need cryocoolers, we need power supplies, we need vacuum systems. So there's always old technology that fits in with the new technology. And then you have to think about the market in the broader sense, the value that you're bringing to people. How are people going to use this? Why are they going to change their behaviour to use technology the way you think they should use technology? And that may be very broad. It may be something environmental even. It doesn't have to be a product. But somebody has to change their behaviour and support what you're doing in a sustainable way. And then you have to implement it. So you need the business models, you need intellectual property, you need the manufacturing technologies to do something. And these things have to work together. So part of my job as the director is to think holistically about what we're doing and whether it's feasible, what we're working on. We can bring these things together, develop technology with a view to how it can be implemented. I just want to give you one fun example because I think it's humorous, I guess. The wheel was invented in 4000 BC. The bag was invented in 3000 BC. A useful bag with wheels was only invented in 2000 AD, and this is really true. I was at Vic House in my first year of university. I had a bag with wheels. They were completely useless wheels. Of course, they broke, they buckled. I had to haul my bag down to the railway station. I remember you'd carry your bag in one arm, it'd get tired, and you'd change to the other arm. So it was really true. What changed, though? If you think about what changed, obviously materials have changed. There are better plastics, tougher plastics which can survive as those wheels. There are better and cheaper manufacturing technologies which can produce them at scale. There's better design in here. And I think the market has probably changed. This could be taken up quickly. There's a mass market in transportation. And everybody's trundling these things around the airports of the world. So what happens in technology is often a bit unpredictable, and it changes with all of these factors. So there are now fusion companies that think they're really going to do it. They're going to make fusion devices which are smaller, more compact, higher fields, and they can iterate faster. And they've got a lot of money. So this one in particular out of MIT has raised about $2 billion to do this. This is their coil, so it's much smaller than those ITER coils, which were, the size of more than the size of this room. This is about 3 meters. You can see the cryocoolers connected to this. I mention this in particular because some of Robinson technology is going into this coil. We're working to integrate our temperature sensing technology in order to monitor the coils and make sure that no part of them is heating up. So we've been working with Commonwealth Fusion Systems in Boston for about 4 or 5 years now on different aspects, and they are moving very fast. So it's a very exciting partner to be working with for the Institute. There are also many other private companies. You'd be surprised how many. I'm surprised how many there are. I've just put one down the list there, Watch This Space New Zealand. So I don't want to steal anyone's thunder, but something may be announced. I'd like to move on now to talking about electric aircraft. And this is a picture you may have seen recently, Air New Zealand announcing that they are really going to be pushing electric aircraft in order to get to zero carbon. Now the aircraft here you're looking at are small. They'll take half a dozen passengers maybe or so. And so battery technology can work reasonably well at that scale, as long as they're short distance as well. So a few passengers, short distance, maybe going to Nelson, batteries can possibly work. But as you scale up, you have to think differently. And what you need is something much more like the Toyota Prius type system. So you're going to need a fuel, and it's going to have to be carbon neutral or carbon free. So it might be hydrogen or ammonia or some other carbon neutral fuel. And then you'll have a motor, but like in the Prius, the motor actually works more as a generator. So you can think you've got to have a generator which will generate electricity. You'll have batteries to manage power, but you don't want too many batteries. And then you want motors that actually drive, in the Prius, drive the wheels, and an aircraft drive the turbofans. So you end up with concepts a bit more like this. So these are two concepts being promoted by NASA. So in which you may have a number of turbo generators distributed in the aircraft, and then a number of superconducting motor-driven fans. So you use superconductors in both the generators and in the motors to drive the fans. And with this technology, you can actually have, that 737 and above class aircraft becoming electric. So the fundamental reason is that current density. So here's just a comparison of two motors. These are actually ship motors, but a conventional motor at 36 megawatts and a superconducting motor at the same rating. So you can cut down well over half the weight by taking out all the iron and copper in a conventional motor and replacing it with those superconductors. So even though there is an overhead with the refrigeration, it's more than made up for by taking out that iron and weight. And the engineers working on this are convinced among themselves that superconducting motors are the only way to do this. So this is the concept we're working on. So a little bit more for the technically minded to understand. So a basic alternator, you can think of it as a magnet rotating inside a stator wire. And then you can think of adding a yoke, which means just some iron which extends where that field is projected. And then you can extend that yoke into 3 dimensions, extend it a little bit more. And then you can take the very interesting step of actually taking the magnet outside the stator wire. So the source of the field becomes on the outside and it can become static. So that's a big advantage. So the inner rotor can now be a piece of iron which can rotate extremely fast and be very stable, and our superconductor can be static on the outside. Rod and his team have been building this motor over the last few years. This is what it looks like in actuality. So the white wires there, the white insulation, those are those stator wires, in which the rotor is going to rotate. And on the right-hand side there is the steel rotor, which will rotate at many tens of thousands of RPM. And here is the team with the magnet put together. So it's just being tested this week, actually. I checked in with the team. They didn't have any data for me to present, but it's really a fantastic achievement to get this going. So Rod here, he looks like he's holding a part that's been left over when they've put it together, but actually that's the superconducting coil which goes into the centre of the magnet there and on the outside of that structure. One other transportation application I'd just like to mention, this goes back away probably 10 years, or may have started 10 years ago actually. We worked on a traction transformer, so this is a train transformer for the Chinese railways. So this is an excellent application of superconductors for exactly the same reason. So trains have large transformers on them, these high-speed trains. They're about 6 MVA rating. And with superconductors, you can take out a lot of the volume, a lot of the mass. You can increase the overall efficiency. So hence, actually have more capacity in the train to carry passengers rather than carrying the weight of electrical equipment. So this project has been somewhat stalled on the Chinese side, but we came up with an excellent design for this, and it was, what else can I say? We did some very good work in developing that design, and hopefully this will come to fruition in the future. Okay. Now I'd like to talk about superconductors in space. So because of this quality of superconductors having much higher power density and being lighter weight and less mass than conventional conductors, you might think they're very good to put into space, and we think so as well, or at least it's very much worth exploring. What can we do with magnetic fields in space? One thing you might think is, space is cold, so that's even better, so you don't need so much cryocooling. Actually, interestingly, that's not really true. So in low Earth orbit, for example, the average temperature of those satellites is roughly room temperature, which when you think about it is not so crazy, because they're in the sun half the time and then they go out of the sun, but they're rotating in and out of the sun every, say, few hours. So they average out to about room temperature, and the electronics and so on that goes into them is generally similar to electronics on Earth. Also, you want to be in the sun because you need some power. You want solar panels and you want power to do things. So the cryogenics is not you can't take advantage of the cold of deep space, at least if you want to do things around the Earth. So you have to model, and this is a model here of the solar radiation that you get. You also get infrared radiation and reflected radiation off the Earth. So you have to model all of that. This is some very nice modelling done by Jamal Olatunji. So we just looked, first of all, at a small satellite and how that would behave. So first of all, this is with no solar panels or anything. It's just the sort of ambient effects, and you can see it sort of oscillates, around zero, maybe roughly, as it rotates around the Earth. Then we added solar panels to this and said, okay, now we're generating some power. We're going to use that power to run our cryocooler. So can we get enough power to cool our magnet down and make it operational? And the good news is yes. So you can see the blue line, which drifts down, says the coil is cooling down over time. In this case, it's about 10 hours, so it's quite slow. So it isn't easy to cool things down to an operational temperature in space. It's something you have to engineer quite carefully. But this demonstration showed that it could be done even on a fairly small scale. And generally, as the scale gets larger, it gets a bit easier because you've got more power to play with. You can have larger cryocoolers, more efficient cryocoolers, and so on. So that was design success. The green area on the right here shows that we can get down to our operational temperature. It is important about where you put radiators, so any heat that you generate in the satellite has to be radiated back to space. So we don't have water cooling or air cooling, the kind of things you take for granted in the laboratory. So what are we going to do with this? So the application that we're looking at first is electric rockets. So these aren't rockets that will take off from the Earth and get you into space. They're rockets that produce relatively small amounts of thrust, but they're used to move about in space. And the great advantage of them is that you can use the energy from the sun to accelerate ions, particles, and use that to push you along. And that's much more efficient than taking up large amounts of chemicals and burning them to take yourself from place to place. So for example, if you wanted to go to Mars and come back, you have to take an enormous amount of chemicals to, first of all, get you off the Earth, push yourself to Mars. Then, of course, you've got to stop before you actually crash into Mars. You've got to slow yourself down, which takes energy. You've got to get off Mars again. You've got to get back. All of that, and you've got to slow down when you get to the Earth. All of that would take an enormous amount of chemical energy. Whereas if you can use the energy from the sun, everything becomes a lot easier. So that's why people want these electric rockets. So they're called a magnetoplasmic dynamic thruster, is what we've been working on. So it looks a bit like this. So we have our magnet to help accelerate those ions. And so the bigger the magnetic field, generally, the more we're accelerating those ions and getting more thrust. So people are interested in these because they're very fuel efficient, because you're accelerating them, and they're good for high power systems. So this is a magnet that we developed for a test that we did recently. This is our test system, so you need a very large vacuum chamber in which you can test this thrust, that it actually works. So a great effort for the team getting this up and running and the test equipment. We recently been collaborating with Nagoya University, and I will now show you an electric rocket in operation. There we go. So that's it sort of being switched on, and a big pulse of plasma being created as the system is energized. So this was using our magnet. So we've made very good progress on this technology, and we're continuing to develop that in our laboratory here. The next step for proving that we can take this into space is to do a magnet mission to the International Space Station. So we have signed up with a company called NanoRacks, who work with NASA to put experiments on the space station. And we're going to deliver a magnet to them in 2024, which will be taken by the astronauts up to the space station. It'll be mounted on the side of the space station. It isn't a full thruster system because that's a little too complex for us right now, but we will have radiation sensors there to look at how the magnetic field affects the radiation environment. And we'll also be fully testing the operation of the magnet, so how our cooling works, how the amount of power we need, how long it takes to cool the magnet down, and ramping the magnet up and down in field and so on. So that's a very exciting project. It's probably the most ambitious project we've undertaken to date at the Institute. So we're all very excited to get that going in 2024. One other project we're doing in space at the moment is a magnetic heat shield project with DLR, the German Space Agency. So when you interact with when a spacecraft is re-entering the atmosphere and it hits the atmosphere, it forms an ionized plasma because of the heat of re-entry. And with a magnetic field, you can sort of push that plasma away from the aircraft and shield the aircraft somewhat from that heat. So we are building a magnet which will be taken to Germany to be used in one of their test facilities. So they have the test facilities where they can produce a plasma flow which simulates that effect of hitting the atmosphere, and we'll be testing whether whether or not it works, and it actually is a technology worth pursuing. There are many other interesting applications of magnets in space. One of the ones we are keen to push is shielding, magnetic shielding. So one of the unsolved problems of going to Mars, for example, is the solar radiation, which can be very dangerous to humans. So at the moment there's no real system to shield from that. Actually on the International Space Station, the astronauts actually kind of hide behind the luggage when there's a solar flare and the danger of solar radiation. So they basically go to somewhere in the space station where there's the most mass possible between them and the sun in order to protect themselves. But once you think about going to the moon and having orbital stations on the moon and so on, you really need something better than just going and trying to hide somewhere. Or having a lot of lead shielding or such like. So having a magnetic shield would be a fantastic solution. Okay. So there are many other things I could talk about, but I think I'll draw it to a close there. We're working on some fantastic technologies. We've got some fantastic staff who have helped us develop all of these projects. And we are really looking forward to seeing these come to fruition, see them become real things in the world and proving what we're good for. So, nō reira, tēnā koutou katoa.